Hi everyone, please give a round of applause for our next speaker, Harshal Shah, Senior Software Engineer. Please, if you have any questions, we'll answer them at the end. You can scan the QR code and go and put your questions in Slido.
Awesome. Thanks for the introduction. Before starting the presentation, just a legal disclaimer. The views, opinions, and content shared in this presentations are all my own and and doesn't represent anything like any views or opinions or positions of my employer. Okay. Good afternoon, everyone. I'm Harshal. I'm going to talk about pets, not the one which you love to cuddle at home, but privacy enhancing technology. And thank you so much for coming today on a Sunday afternoon. You could have chosen to be somewhere else doing something better, and you chose to be here. So thank you for that. Yeah. As you all know, like data is the new oil. Everyone is using it in some way. And we are already moving into a reality where applications are using data in all sort of way. And the way we are using is in a way where we are collaborating over the data. What if we have scenarios where we are trying to collaborate over data and we don't trust parties, like different parties which we are collaborating? There are few concerns about those collaborations, and few of them are listed in the slides. One could be like computing, parties can cheat, which is basically parties trying to learn more information than what they were intended to learn through interaction, or parties can just go like in completely arbitrary manner than what they were intended. So instead of during the interaction trying to send the actual value, they can just send some garbage value, or it's even possible that subset of the parties can collude and try to like take over the interaction. And in general, this concern has become more and more real. And that's why we had an executive order passed back in, I think, 2023. And this order calls for technologies called privacy enhancing technologies. And some of them are listed in the slide. And these technologies are like secure multiparty computing, homomorphic encryption, zero knowledge proofs, and the list is pretty long. Okay, give me a cheer if you have heard at least one of this technology. Okay, I'm happy that people are not people are still awake and they are not asleep by now. Okay. In some sense, this privacy enhancing technologies are not new. The genesis of them have been started from like 1980s, and we are around like 35 years into their initial conceptions. And one of the popular, like common misconception about these technologies are that they are purely economic and they have never seen like light of day, and it's not used in used by like general public or general company. But this is in fact not true. Privacy enhancing technologies have made their debut and recently in past 5 years, and some of the examples are mentioned in the slide. I think back in 2018, Zango introduced their MPC-based wallets. Then Microsoft and I believe Google is using FHE, which is full of homomorphic encryption, for their password use case, where they are trying to see if your password, like customer's password, is part of a data breach or not. Then companies are also actively working on custom libraries, which are highly tailored for large-scale applications. And there is one example actually I forgot to mention in the sliders, which is very recent, which is from Apple. Apple is like big, as everyone knows, is big on privacy. I think last year they introduced a private call ID lookup scenario where they are using again like homomorphic encryption for doing some sort of privacy. And we are already in the reality where pets is already out there, and it's getting more and more serious. Okay. So I would like to demonstrate how a privacy workflow might look like. Okay. This is an example of election. And we have, in this election, we have two parties, like two candidates, sorry. One is 0 and 1. I know the names are pretty dumb, 0 and 1, but just for simplicity, I'm having two candidates, 0 and 1. And we have 18 different voters whose objective is cast a vote, and their votes are displayed in the screen below their icon. Okay, so how can we do this? How can we do an election? Popular way is to have a secure election officer, like trusted election officer. And the job or the responsibility of this election officer is to collect all the votes from all the voters, collect them up. And if in this scenario, if the sum is greater than half, which is 9, then candidate 1 wins. If it's less than half, then the candidate 0 wins. And for this scenario, like since we have 10, which is summation of the votes is greater than 9, it means a candidate 1 wins. What if we have a scenario where we don't have a trusted election officer? Can you do this? Yes, we can. We're going to use a technology which is out there and which is everyone is using right now. It's called encryption, just a basic encryption. And here, the red box represents encryption of that particular vote. So encryption of 0 is represented by red box 0, and encryption of 1 is represented by red box 1. In general, encryption is totally random. You can't see what's it is trying to conceal. But just for pictorial reason, I'm showing it here. In some sense, you can think encryption as in you're adding one layer to try to conceal a secret. And whenever you want to reveal a secret, you sort of remove that layer to see it. Okay. I'm going to use an encryption which has a little bit special property. And this property is even when you add those encrypted values, the encryption of the underlying secret also gets added. So it has a little bit more fancier property. It's just you can add the secret even though we are in encrypted domain. Okay. And for this scenario, what we can do is each person will start just adding. There will be a centralized location where we are trying to collect all votes and just add them up in a secure way. And what secure way is just encryption of take first vote, which is encryption of 0 plus encryption of 1. It results into encryption of 1. Go on. Let's do encryption of 1 plus encryption of 0. It results in encryption of 1. And encryption of 1 plus encryption of 1 is encryption of 2. And by that, we have successfully created encryption of 10 without ever using a trusted third party or trusted election officer who will collect the votes for us. And if it's possible that in this voters can cheat and things like that. But since we are using the special kind of encryption, which sort of adds those values, if anyone had cheated, then the result won't be like in between 0 to 18. And that way you can prove that, okay, people are not cheating. But that's a little bit out of scope for this slide. Okay. So this could be one of the workflows where you can use privacy or not encryption to solve one problem. Yeah. Now let's see. What is fully homomorphic encryption? Fully homomorphic encryption is just the encryption which I mentioned in the previous slide with little more fancier properties. So we can not just add like 2 positive numbers, but we can do like 1 positive, 1 negative. Then you can even like you can not just do additions, you can do other things like multiplication, then subtraction, divisions, and all sort of properties. One thing to notice, all those operations are not created equally. So operations like additions, subtractions, they could be cheap, but doing multiplications could be a little bit expensive. When I say expensive, computationally expensive. And the genesis of homomorphic encryption came into picture when there were clients who had some data like input, and they didn't have the enough compute power to do something. So they wanted to offload their computation to some third-party server. Now, the trivial way for doing this is like just share your plain text input to the server, and it can do some computation. But the problem is like you lose the privacy. And that's where like the genesis of this homomorphic encryption started. You might be thinking that, okay, why is this guy only talking about like very basic operations like additions and multiplications? Like real world applications like neural networks and large language models are really big, and they are not just additions and subtractions, but any applications can be broken down or can be transformed into a lot of these trivial operations, uh, namely additions and subtraction, multiplications. There are some caveats to it, but majority of the cases you can break it down. Uh, and it's also one statement which is true is all these transformations can be also a little bit expensive, but there is research going on out there, like where people are actively researching on how to make this transformation faster, and not just the transformation, but even the encryption or FHE in general faster. Like I've seen companies working on like hardware level acceleration, where they are designing specific chipsets which are highly optimized for their use cases. Yeah. One thing to notice, yes, it's true that a lot of the large language model, like training a large language model in an encrypted domain, might not be feasible right now with the current computational power we have. But what I've seen in past is like from past couple of years, like we have seen at least 2x or 3x performance boost on what's happening underneath. So I'm pretty sure in the next couple of years, it's possible that we could eventually be in a reality where we can have large language models which are which uses FHE for training. Okay. So let me give you a real world example of where we can use FHE. There are two different parties in the slides. One of them is advertiser, and second one is a retailer. Advertiser wants to query whether the customer ID MNOP 3456, not whether, sorry, wants to know how much this particular customer ID spend on that retailer on that particular day, which, as you can see, trivially, it's 16. There are two trivial ways to do this lookup. One is the advertiser can send this customer ID in plain to the retailer, and retailer can do a quick lookup inside his database that, okay, this guy has purchased or spent like $16 or something, and give that query back to the retailer. But the problem is, give back to the advertiser. The problem is, in this scenario, the retailer learns what advertiser is trying to query for. And other trivial scenario is, which is again really bad, which is the retailer sending the whole database to the advertiser and just advertiser doing a local lookup. The problem is, in the scenario, the problem is advertiser is sending a lot more data or a lot more information about the customers than what it's supposed to or what it's intended to. Okay. How can we use homomorphic encryption to solve this problem? What the advertiser can do is encrypt its query, which is the customer ID in this scenario, and send it to the retailer. What retailer can do is, for each of the rows, it can compute subtraction of their customer ID to the queried customer ID, multiply it with the spent amount, and then just add them up. The resultant thing is encryption of 16, which goes back to the advertiser. Now the advertiser can use one of its decryption key to decrypt the result, and voila, we got 16 back. Now we solve both the privacy problems. First is the retailer doesn't need to share all the data to advertiser, and the retailer never learns about what the advertiser queried for. Okay. Second technology, which privacy enhancing technology, which I'm going to talk about, is secure multi-party computing, and it's a very generic term for collaborative computing. And every time if someone says let MPC, they generally refer to secret sharing based MPC. Yeah. So what is secret sharing? Secret sharing is just a way to, as the name suggests, share the secret. In this picture, we have number 5. which is our secret, and we want to divide that secret into two different parts. The way I have done is just split that from the diagonal, and we have two secrets. In general, secrets are pretty random. You cannot derive anything about the secrets or anything about the number 5 from the secrets. For the pictorial reasons, I have divided the secret 5 in this fashion. Yeah, I know it reveals a little bit information about 5, but just for example purposes. Um, okay, so it's not like okay, for like I was just talking about how to share the secret in two different shares, but this terminology can be extended for like any number of shares. This is the way like you can do it for 3 parties. In general, the number of shares or number of times you want to split depends on how many parties you're trying to collaborate with. So suppose there are like 5 different companies trying to collaborate on something. They have a secret secret sharing base like like 5 secret shares. And it's also like it's not necessary that each of the shares are mutually disjoint. So it's possible that each of the shares can have more information than it is supposed to. So in this slides, we have like each share represents like 2/3 of the original secret. So we don't even need all the parties to collaborate to compute something. In this scenario, we can have like 2 out of 3 parties, and we can regenerate the secret back, which is like first 2 or first or something like that. And this is in general called T out of N secret sharing, where T is a threshold which is needed out of N, which is obviously T is less than N, needed to reconstruct a secret. Okay. What would be a secure multi-party computing workflow look like? The objective in this is we want to securely compute addition. There are 2 parties and one party has input X, second party has input 3. Trivial way to do addition is just share your inputs to each other and like just do addition over it. But there can be scenarios where parties cannot share that information with each other. What we can use is the secret sharing. Both the parties secret share their input, split them up, and share with each other. Now, addition is usually like very cheap. When you're doing MPC, you do some local computation, and voila, what we have is secret sharing of 8. Again, just for pictorial reasons, we have answer which is revealing in the shares, but in general, the shares look pretty random. Now, we have the resultant shares. What we can do? One is both the parties can exchange the shares and reconstruct the secret. That way, you have number 8, which is generated. Or you can design the workflow in such a way that only one party can learn about the secret. Or it can be that, okay, neither party learns about anything. This can be something like an intermediate workflow where this can be used for the further computation or something. Similarly, what if you want to do multiplication? First thing is, oopsie, sorry. So if you want to do multiplication, first is secret share your inputs, share with each party. Multiplication is not trivial. You can't just do it locally. You need to introduce something like communication, which requires you to send like 1 or 2 extra messages to compute secure multiplication. But after doing some communication, you can generate 15, which is answer in this scenario. So apart from just doing some basic operations like addition and multiplication, what can we do? Let's talk about synthetic data generation. It's not directly related to pets, but synthetic data generation is just an artificial way to generate or mimic real world data, which doesn't reveal anything about the underlying data itself. So you're just trying to generate like fake data out of the data which you already have. And what you can, and in this scenario, there's 2 parties, just continuing from the scenario of advertiser and retailer, we have 2 parties who have data set A and B, and what they want to generate is a synthetic data, which is combination of which mimics combination of A and B mode. Now, again, the trivial way is if both the parties can share this information to each other, they can share and generate the synthetic data. But imagine a scenario where there are some rules or regulation like GDPR or something which prohibits companies from sharing this information. You can use MPC in the scenario where you first secret share the data, use a specialized MPC engine to compute synthetic data, and we will have secret sharing of D, which again you can use for the workflows. Similarly, you can also do secure inference. I didn't put example of secure training because again it's pretty expensive, but currently we have algorithms which can do secure inference pretty efficiently. In the scenario, what people can there's one client with input X and there is a company with model M. What they can do is secret share their input X and model M, and the objective is to generate M over X, which is M computed with input X, and they again can use MPC to do some communication and generate M over X. I'm not going to go too much into detail, but there can be so many different scenarios for a secure model inference where the input X itself is secret shared with multiple parties. The model itself is secret shared with multiple parties or multiple servers. And there are so many use cases, like combination of those. One concrete use case which I want to talk about where people are actually using MPC, which is in a custody wallet setting. In cryptocurrency, what we have is a client which has a secret key, or a client which has a wallet which contains a secret key. Generally, that wallet is sort of hosted by a wallet provider, which is again a third party. And there can be scenarios where the client has to prove the ownership of the wallet, which is basically generate a signature using the secret key which is stored inside the wallet. And it can use the secret key to generate the signature. But the problem is this wallet is a single point of failure. I think, I don't know how many people have seen Silicon Valley where I think there is one guy, or not even Silicon Valley, there was some guy who lost his Bitcoin key and is trying to go through dumpsters to figure out where his secret key is in the dumpster or something. But the point is this is a real problem, having a single point of failure. So what we can do is secret share the secret key. So here in this example, what we have is the secret share, which is the secret key, is shared between three different parties. It's possible that it's one single wallet provider had three different servers, or it's possible that you can have three different wallet providers hosting each of the secret shares. Each of the secret keys, again, random. It doesn't reveal any information about the secret key. So even if one of the servers is get hacked or something, you don't lose your key. And it's also I've seen some cases where a user itself can have custody of the key, where one of the secret key is hosted by client's mobile phone or personal wallet or something. What they can do is do a MPC based interaction to generate a secret key, and then not secret key, to generate a signature and respond the client back with a signature of message M, which is sigma in this scenario. Now, during the animation, it might look that, okay, the secret key and the message everyone are combining at one place, and then it's generating the secret key. But in real world scenario, the secret key never leaves the server or the location. It's just for pictorial reasons I'm showing it here. So they are safe, stored in some hardware. One thing we should think about when you think about MPC is availability. So even if we have a scenario where one of the servers or one of the companies is down, you want your client to generate a signature even when one of the things are down. So in this scenario, you just need since this is 2 out of 3 secret sharing, you just need 2 of the servers to generate the secret So I'm just using like first and the third one to generate the signature. You can also use the second and third one. So in general, um, if you want to generate, like if you want to think about MPC workflows, like I would say there can be cases where you want like 100% availability, and MPC can help you get that availability. Yeah, I'm good. I'm done. So I'm happy to answer any questions you have.
And then I think for now we have one question. Please feel free to add more if you have any. When should we use MPC over FHE?
Oh yeah, that's a good question. So when you have when like as I showed in the slide, you're okay to offload the computation to a server where your client doesn't have enough compute power to do something. You can use FHE, and when you're okay where you have some latency in the sense like uh, you want to be the part of the interaction, but you're okay that it might take a couple of milliseconds extra to generate something, then you should go for MPC. So compute, think about FHE, latency, and think about MPC. That's my way of thinking.
So we have another question. What paths do you think companies should start with if they're not using any yet?
So what I've seen in general industry adoption is people are starting with FHE, fully homomorphic encryption, like Apple, Google, Microsoft. If you see even IBM, they have some specific use case where they are using FHE, and I think MPC adoption is also taking place, but it's just a little bit slower.
And the last question, can you speak to the utility versus compute trade-offs of using a PAT instead of non-PAT solutions?
So I think it's not exactly apples to apples comparison when we talk about pets and not non-pet scenario. If there is a option where you can do things in plain text, which is not using any of this privacy enhancing technology, go for it. You cannot like it would be definitely 10 times slower or computationally expensive to do a lot of these operations. But the real comparison is, what if you can't do any of these things? What if there are like geographical restrictions, where there are certain regulations where you can't get that data? In that scenario, the comparison is either you don't get anything or use this pet solutions to do something. So that would be one way to think about this problem.
And we have the last question. That's I think for the time that we have, because it's someone else said, please answer that. What about federated learning?
Yeah, federated learning is also can we think about like a generic term of secure multi-party computing, and it depends on how federated learning you're using. Like people in general use, like when you're talking about federated learning, they use like referential privacy on top of it, but I don't know what the question is intending for. Like I'm happy to answer that question offline, but yeah, that's it.
Actually, you were fast, so we have. I'm not sure if you have time to answer that, but what are your thoughts on privacy washing by companies using pets to do things that are against users' interests?
I mean, again, this comes in the scenario where consent plays a really important role. Like, yes, you can use privacy enhancing technology to break the privacy of a user, yes, but we should have a consent level which obviously like doesn't bypass this restriction.
Well, thank you. Please give a last round of applause for Harshal.